Thank you. And thanks for having me at this wonderful forum. I think this is a really, really good idea to have this morning coffee tradition. So my point of view today is to explain to you a little bit about ill-post inverse problems and their connection to machine learning. It's a really strong connection and only growing in importance, I think. And just a quick add, of course, I'm representing our Center of Excellence, whose goal is to cover the whole of Finland with inverse problems research groups. As you see, a good part is already covered. This is my plan today. I'll say a few words about the connection between inverse problems and AI. Then I'll show two different forms of tomographic imaging and comment a little bit about machine learning type advances, and then I'll conclude. So in inverse problems, this is the way we think. We have some kind of object we are interested in. We don't have a direct access to it, but we can measure it indirectly in some way. So we get some kind of data about it, and then we want to extract some information about the object. Maybe completely, but not often it's not possible. But anyway, some information. I think this already looks quite a lot like machine learning. But ill-post inverse problems are a special type. This inverse problem is not ill-post. This is well-post. It's very simple. Our object is a black and white photo, pixel values between 0 and 1, 0 black, white, 1. This is just a negative photograph, or if we subtract all pixel values from 1, we get this. And if this is our data, we can perfectly get back here by subtracting these pixel values from 1 again. So it's a kind of an inverse problem, but a very easy one, and there is pretty much nothing to do. This is an example of a much more complicated problem where we have blurring of the photograph, so misfocusing, and then maybe shot in poor lighting, so it's also a very noisy photograph. So this is the problem of deconvolution, and this is an ill-posed one and really difficult to solve. And anyone specifically interested to this one, I'll advertise my new course given last fall, the first time, Inverse Problems 1, Convolution and Deconvolution, kindly accepted to the Data Science Master Program. Okay, Peter Maas, my colleague from Bremen, Germany, has been diving deeply into the connection between machine learning and inverse problems, and I especially like his approach of studying first very simple ones and seeing already the characteristic trouble that arises. So he defined this matrix with a positive epsilon here, so the matrix is invertible in the mathematical sense, no problem. However, it's very, very close to a singular matrix. And the smaller you take epsilon, the more unstable is the inverse of this matrix. So he just created a lot of training material with 2 vectors x and 2 vectors y connected by this simple equation, and I think it's yet to appear, but I think it will appear soon, his report. Actually, I've seen it a couple of times in conferences where he shows by quantitative measurement that it's much more easier to learn y from x than the other way around. So somehow the inverse of this matrix is very unstable. Of course, this is now a very, very simple problem, and in practice we are dealing with much larger dimensions in the problem, but the underlying trouble is the same kind. The matrix is not so well invertible. So X-ray tomography, you may have seen machines like this. It's a modern workhorse in hospitals. The idea is to rotate around the patient and from each direction shoot a bunch of X-rays, and you can measure how much attenuating tissue there was on the way of the X-ray. So we get these kind of profiles from all directions. Then a mathematical algorithm collects the measurements together and produces a slice image through the person's head. This is a very classical inverse problem. Cormack and Hounsfield got Nobel Prizes in 1979 for solving this one. Let me quick tell you how this works. So here we have a much simpler object consisting of 2 disks this is the profile data from 2 disks. So how would we do this inversion? It's based on back projection the data back to the image domain. Here I'm showing only 7 directions. Actually what we do is we use all the directions and we back project the data. We get the original back, but only in a smooth way, and then we use FFT. We take the smooth image to the frequency domain, we multiply it by the frequency variable, and actually then we have a theorem saying that we get perfectly the original picture back. So this is what happened to the head slice I showed you. So this is for traditional X-ray tomography. Well, yeah, this is again this one. Let me skip that one. So in my research group, it's a big topic to try to do X-ray tomography with less and less images, less and less data, because in X-ray tomography, irradiating the patient delivers some radiation dose, which is unhealthy. So it's better to image with less radiation. So we made this kind of a little experiment. We imaged the walnut from 1200 directions. And when I apply the process I just described to you, we get this very detailed image with these sub-millimeter features very clearly visible. However, if we have only 20 images and we use the same algorithm, we get this image. Well, of course, this method is not designed for such sparsely collected data, so we get a much worse image. Now, in traditional inverse problems, there is a bunch of methods that have been designed for this kind of missing data problems. This is, for example, total variation regularization, looking for the best piecewise constant image matching the data, and also having the shortest possible boundaries between these constant areas. Anyone interested in this? Welcome to my course, Inverse Problems 2, Tomography and Regularization, also every fall. Please send your students. Okay. Anyway, of course, one can apply machine learning to this, and I would like to mention that Jonas Adler and Ozan Öktem at KTH in Stockholm, they were the first to try deep learning methods, at least among the first. Anyway, they made a seminal contribution to the field because deep learning with convolutional layers is of course a very good approach for deconvolution. So if your data comes from convolution, I think CNNs are really well designed for dealing with that. So actually, the trouble in this image can be seen as convolution with a specific kernel that looks a little bit like a star. So they got really nice results in inverting that. And inspired by their work with Gitta Kutoniuk and Maximilian Merz and others from Berlin, we tried a little bit more challenging problem where we can image the patient from certain directions, but some other directions are not available. This happens in many cases like dental imaging or mammography, where the machine cannot go all around the patient. So then what typically happens is that we will miss this part. We don't have X-rays that go this way. So this part here, which is the detail from here, we can't see. They are missed. So when our rays end, we get these artifacts or errors in that direction, and we don't get these parts recovered at all. There's a precise mathematical understanding what can we expect to see from the data, and for a long time people just accepted that we have to deal with this kind of artifacts. However, machine learning, we used so-called shearlets, that is transformation a little bit like wavelets that can especially well follow curves and analyze where does the target have jumps. And then we trained a network to understand the relationship between known parts of the curves and the unknown parts. And then once the network was trained to know these kind of things, we can actually pretty nicely recover these missing parts with lots of potential applications in new kinds of X-ray tomography imaging. And then I'll switch to another, actually even more difficult and ill-posed imaging method called electrical impedance tomography. It's my long-time favorite. I did my PhD thesis about this topic, so it's been with me for more than 20 years. There the idea is to feed electrical currents to the human body. For example, aiming to image the heart and lungs, then we would put, let's say, 16 or 32 electrodes around the chest like this. We feed in currents, we measure the voltages that arise, and our aim is to have a picture where we see the heart and the lungs. So lungs with air are poor conductors of electricity, so we see them as low conductivity, and the heart filled with blood conducts better, so we see it as high conductivity. This has lots of potential applications, including Jennifer Mueller, my longtime colleague from Colorado, has made a lot of progress recently in cystic fibrosis studies where the patients suffer from very sticky mucus in their lungs and they can't breathe properly, and the doctors they want to measure very precisely how much air is going into the lungs and how much not, I mean, compared to healthy ones. This can be for adults, this can be done with this kind of spirometry measurement, but kids can't do it. So for small children, actually this is a safe method that Jennifer has been now testing with good results. So it has kind of several medical applications. So the idea really is that if there is 32 electrodes, the idea is push some current through into the material and then take it out from others, and the idea is to apply several different current patterns and measure the voltages corresponding to them. And why is this thing ill-posed? Let me quick explain the mathematical model here. So this is now for a two-dimensional patient, so this is the unit disk omega, and inside the unit disk we have a function sigma that has big value where electricity can flow better and small value where it's much more resistive. And we assume that this is not zero, so we exclude completely non-conducting parts. Otherwise we could hide something inside a non-conducting annulus. So we exclude, and usually in the human body that's not the case. And also we think that there is some maximum value for the conductivity. So then we are dealing with this kind of partial differential equation. We think of applying a voltage F. So F is a function defined on the boundary, how much voltage there is at each point at the boundary. Then inside the domain, conductivity times gradient of U. U is the electric potential inside. Sigma gradient U with a minus sign is the electric current vector field inside the domain. And since there are no sinks or sources of current inside, the divergence of the vector field is zero. So this is a mathematical model introduced by Alberto Calderon in 1980, and he made this precise mathematical question. If we know this operator, so this is a model for all possible measurements, so for any voltage distribution at the boundary, this operator tells us what is the electric current through the boundary. So it's rather interchangeable, feeding currents or applying voltages. The theoreticians want to apply voltages and measure currents. Practitioners want to feed currents, measure voltages. It's almost the same thing, not a big difference there. But let me just briefly introduce how this ill-posedness appears in this problem. So here are two patients, two-dimensional, rather simple patients. This person has some kind of trouble with this left lung here. I don't know what really is going on. I'm not a doctor, but looks bad. Yeah. So let's measure these patients. So let me take an angle theta from 0 to 2 pi around here, and I will apply the voltage cosine of theta. Apply it at the boundary. And now what I'm showing to you in these pictures is the voltage potential inside the patient. This is something we don't see in practice because we measure at the boundary and we don't cut the patient open. That's the whole point. We want to measure without harming the patient. But this is what nature does. This is how the potential acts inside. What we measure is now the current through the boundary. For the blue patient it looks like this, and for the red patient it looks like this. Rather similar. Let me overlap these two measurements for you. And we see that here at an angle a little bit bigger than pi we see some difference. Elsewhere not so much. And why this angle? Well, this is 0, pi over 2, pi, and in this area is the little over pi angle. So in that area we see that the measurements don't quite overlap, which is only natural, of course. Then we could apply a different voltage. Remember, we apply different patterns. So here I'm applying cosine 2 theta, a little bit more oscillatory. So it has maxima and minima like this. Again, we get different measurements, but not very different. If I continue applying more and more oscillatory voltages at the boundary, kind of with the idea of applying a Fourier series to approximate any function, you see that the more oscillatory input I use, the less and less we have any difference between these two. And just to give you an idea, in practice we always have measurement noise. So our measurement is a little bit noisy. So this is the situation in electrical impedance tomography. We need an algorithm that when fed the blue curves as input will produce this image. However, when fed the red curves as input, it will produce this image. As you can see, there's a situation that there's a big difference between the objects, but a very small difference between the data we have about them. This is ill-posedness in inverse problems. It's very unstable going from these noisy measurements reliably into these images. And remember, these are meant for the doctor that then makes really important decisions about the life of the patient. So this is a really, really difficult problem. So what kind of role could machine learning play here? One favorite idea, maybe my favorite because I was developing this method I'm describing. So actually my PhD thesis was concerned about this kind of special nonlinear Fourier transform I'm showing here. So the basic idea would be that there's a nonlinear Fourier transform and there's an inverse transform. And there is a really important paper in our field by Adrian Nachman in 1996 in the prestigious journal Annals of Mathematics. This paper was the topic of my licentiate thesis. I spent 2 pleasant, wonderful years reading this article of 49 pages. It's a bit sticky. Anyway, what it says is that if we know this perfect infinite precision measurement information, we can put this into a so-called boundary integral equation, and from there we can compute this nonlinear Fourier transform, and then we can invert and we can get a nice picture of the patient. But remember, this is for infinite precision data, which we never have in practice. So then with Jennifer Mueller and David Isaacson, my American colleagues, we made a practical implementation of Nachman's ideas. So here, when we have the measurement matrix with noisy data, of course it's finite now and finite precision. We put this to a numerical implementation of the boundary integral equation. What happens is that we have a stable disk. So inside some disk in the complex plane, we have reliable information about the nonlinear Fourier transform. But outside some radius, we get garbage. This is how, like I showed you, this ill-posedness, how to map from these measurement curves into completely different pictures. It actually, in this nonlinear frequency domain, we can nicely separate the stable information and unstable information. So we did what any reasonable engineer would do at this point. We take the good part, we put 0 instead of the bad part, and we invert. This was a really nice invention in the way that in our field, I think this was the first time to make a really practical imaging method out of these very theoretical advancements in the field. So I'm really proud of this work, and we could even prove later that this is a full so-called regularization strategy. That's kind of the holy grail of inverse problems mathematics. Really happy about this work. Although what remains is the thing that although this image is really robust, I mean, like I showed you these data, these ones, and the challenge of finding the right picture from these two. So what this method does is that it really does find these two different images in a stable way. However, they are very blurred like this because there's a low pass filtering. Although it's nonlinear, it's very close to the actual or the usual linear low pass filtering using FFT. So this is nice what Sarah Hamilton, our former postdoc here, and Andreas Hautman, my former student, they actually used convolutional neural networks for sharpening these images. So these are some real measurements done in University of Eastern Finland, Kuopio campus. So these are the pictures we get with our method. They are blurry. However, Sarah and Andreas taught a CNN network to sharpen these images. Also, this is another thing we did with Sarah and Andreas. This was before any of us really went into the machine learning business. We had this idea already 2014 that this is now the measurement matrix we have. So this is a very simple conductivity background 1, and this is a conductivity 4 disk moving around. This is the measurement matrix, and my point here is that it's rather unintuitive here how the location of this one disk is encoded in the raw data. This is like Teemu said about just the pixels in the data. I mean, we have a lot of pixels here, but how are the two coordinates x and y of the center of this disk, how are they coded here in a very complicated way, I would say. And while certainly this can be learned, maybe with the UNet or with some really advanced machine learning method, I'm sure it can be learned. But if you look at, for example, this one, where we have these so-called complex geometric optic solutions that are kind of generalized exponential functions used in the nonlinear Fourier transform. Here we can actually see, so this is from 0 to 2 pi, this axis. So we can actually read off very clearly what is the angle of the location of this guy. So somehow with the point that I think this will be a much better feature for learning than the raw data. Just to do some nonlinear processing first, get this one, and maybe it's much easier to learn from this to find out where the dot is. So this is kind of my current philosophy in how to combine inverse problems math and machine learning to provide nonlinear features for learning to make it much easier. And now one important application we have ongoing is the detection of or diagnosis of stroke. As you may know, a person with a stroke has 3 most important symptoms. Smile is just one side, speech is incomprehensible, and when raising up 2 hands, only one hand will go up. But these symptoms are the same for bleeding in the brain and for ischemic stroke, which is a blood clot preventing bloodstream in part of the brain. It would be really important to detect this already in the ambulance instead of going to the hospital and doing a tomography, which of course it's all fine and good because then it can be seen, but it would be nice to see it quicker. So we have an ERCO Foundation funded project for going for some kind of measurement device, maybe something like this, to see from the conductivity which one is it. And one of the mathematical methods, we are approaching this problem with plenty of mathematical approaches, but one of them is this one, a recent paper with Alan Greenleaf and Matti Lassas, Matteo Santacesaria and Günther Uhlmann, where we used these generalized exponential functions in a new way that we can actually use virtual X-rays. So there are no X-rays involved actually, But with these electrical measurements and some nonlinear math, we can compute this kind of profiles that for, let's say, this brain here, the blue one here is the skull. So let's say if we enter from this side to the skull, so we see a dip here. This is information coming from the low conductivity skull. And when we enter from the skull to the brain, this jumps up. And then inside, at this point, we see some dip down. But so this is ischemic stroke with low conductivity. This is hemorrhage. So here it would jump up. Showing it like this, we would detect something between this and this. However, this picture here is highly unrealistic, because to get so detailed profiles, we actually, if I go back to this picture, remember we have this circle enclosing good information inside, and outside everything is unreliable. So in that picture I showed you, so I think this radius of this one, I think, is something like 6 in the complex plane. But I used the values up to -60 this way and +60 this way. This is something that can never be done with practical measurement devices. In practice, this radius should be something around 5 maybe. So then what happens is, instead of this one, we would get something like this. But this difference between these two guys, it's just linear convolution, which I think should be rather easy, at least rather promising to deal with machine learning. And we have been studying this kind of examples where we have ischemic and hemorrhage stroke to compute such profiles I just showed you, and with this kind of idea that if we compute the profile from information located more on this side. So we see, so here is a combined effect of the skull and the stroke, and then we compute the same from this side, which is the healthy side of the head, and we get this kind of profile. And now one of the ideas is to just flip this one around, subtract these two guys, hoping that the skull informations will cancel roughly, and then what we have left is only information about the affected area. So that would be kind of very unintuitive for the human eye to say which one is which. But again, I think this is something that machine learning should be capable of doing. And in these very simple experiments with rather restricted locations and types of stroke, even support vector machine can do this with more than 99% accuracy. But of course, in practice, strokes can be of very different sizes, very different locations and all that. So we are kind of working to push it further. And of course, I mean, maybe moving from support vector machine to more advanced machine learning techniques. But to start with, at least to see what is easy and what is not so easy, and what kind of features are the best to draw out from the electric data first. Okay, so the driving philosophy right now in my research group is to offer the machine learning community nonlinear features, because you know robustness is the main thing in inverse problems research. The most important thing, whatever algorithms we make, they must be robust against modeling errors and measurement noise. That's somehow the leading motto of the whole inverse problems community. So I think our mathematics is good for providing machine learning with lots of useful nonlinear features. And we hope for this kind of benefits that maybe we can do the learning with a simpler network and maybe with a smaller set of training data. Also, if we first compute something with really well-known analytical mathematics, like I showed you, for example, these profiles. Here we have very good geometric understanding what kind of information is encoded into these functions. So then when we learn from these functions, the remaining part is a smaller step to do compared to learning directly from raw data. And also, I think I've heard of these examples where a trained network can be fooled somehow by adding some little bit of noise that's invisible, but then it makes the classification wrong. I think when starting with a robust inverse problems technique, that will not be fooled. That's the whole point of inverse problems. They will not care about small perturbations. So after this inverse problems feature extraction, I think the resulting learning should be more robust in that sense. So that was my point, pretty much.